Okay, I want to start analysis of fractional order functional differential equations with multiple constant delays. First of all, we are starting with table of contents, a literature review, statement of main problem, linear homogeneous and inhomogeneous fractional order multi-delay systems, existence and uniqueness of solutions for nonlinear fractional time delay differential system, finite time stability results, an illustrative example, and bibliography. This is the contents of my presentation. First of all, I want to introduce some papers in the existing literature, which is related to our problem. One of the main problems in the theory of fractional functional differential equations is to find explicit representation formulas for solutions, especially in the case of linear equations. Because for delay-free systems, this is very easy, but for delay differential equations, this issue little bit is complicated. Let us briefly summarize what has been done to solve the problem of representing solutions of linear delay systems with integer or fractional order by special functions, which is called delayed matrix functions. We mentioned two pioneering work. First one is belong to Huseynov and Shuklin. Firstly, they have introduced the delayed exponential matrix function e power to a1 times t. Here a1 is e power 2 minus a0 times tau times a1. By using this delayed exponential matrix, they give closed form representation of solution for the Cauchy problem with permutable or commutative matrices. Look at the following system. X prime t is a0 xt plus a1 xt minus tau. Here, tau is fixed time delay. This is positive real number, and this is satisfying initial data. Xt is phi t whenever t belongs to square bracket minus tau 0, and where initial function is continuously differentiable function on the initial interval. According to 1, any solution of system has the following integral form. Moreover, Huseynov introduced into another representation formula, again for the same linear system with permutable matrices using Laplace transform technique. But these issues are related to systems with permutable matrices. For non-permutable matrices, it's extended by me and my supervisor, Huseynov and Mahmudov, in our another paper. This is 3, and we have considered this problem, and we extended delayed exponential matrix function with non-permutable linear bounded operators, especially for matrices. These problems are considered in classical case, differential equations with integer order. In terms of fractional calculus, fractional differential equations, in 4 and 5, the classical results are extended to linear fractional order equations with single constant delay or pure delay using a delayed Mittag-Leffler function. It is known that delayed Mittag-Leffler function, matrix function, is a generalization of delayed exponential function. In 6 and 7, these concepts is extended to permutable and non-permutable matrices, again in 2 papers. One, Huseynov, Mahmudov, another one is considered by Mahmudov. And we get here 2-parameter Mittag-Leffler functions, of course, delayed Mittag-Leffler functions, and also we introduced delayed 3-parameter Mittag-Leffler functions which are the fundamental solutions of fractional order time delay systems with permutable or non-permutable matrices. Explicit representation of solutions to the following initial value problem with multiple constant delays in classical sense, firstly presented by Medved and Pospíšil. Look at here, they exist L times delay, constant delays. So here tau will be maximum value of these fixed time delays. They have motivated by Huseynov's work for single delay. Then they get fundamental solution of system 2, homogeneous system, but their fundamental solution is expressed inductively constructed with k-fold iterated integrals. Since this representation formula for solution 2 is very complicated, this is useful, but in terms of theoretical purposes, not for practical computations, because look at, they exist k times integration. So since in terms of computational results, this integration is very complicated. So in this work, we revisited the concept of multiple delayed matrix function, and this concept is extended to multi-delayed perturbation of two-parameter Mittag-Leffler functions in fractional derivative, which covers classical results. In contrast to the results in this paper, the representation formulas are not constructed by inductively, but depend on some of non-permutable products in the case of matrix functions. So this technique is very useful in terms of estimation the solutions and for other qualitative theory for functional differential equations. Motivated by the above papers, we analyzed the following Cauchy problem for Caputo type fractional order linear differential systems with multiple various or incommensurate constant delays. Here, d alpha is the Caputo fractional differentiation operator of order alpha in 0, 1, but whenever alpha equals to 1, this results is converting to the delayed exponential function. So this case is covering the classical results. AI are I from 0 until L are any real matrices. T is prefixed iteration domain lengths, and without loss of generality, we are assuming that T is n plus 1 times tau for fixed natural number n. Let initial function be arbitrary vector function with components continuously defined on initial interval I, and forced term is describing the external forces, which is a continuous function on J. J is from 0 until T. Then I want to introduce statement of main problem. Our aim to get analytic solution of this problem. What is analytic solution of the Cauchy problem? Analytic solution of the Cauchy problem is understood as a vector valued function xt in Rn defined on L from minus tau until t, continuously differentiable for t greater than 0, less than or equal to t, and satisfying initial conditions xt is phi t for prehistory interval t belongs to minus tau 0. Of course, t is again maximum of tau I is changing from 1 until n. Furthermore, we present several important results on the global existence and uniqueness and finite-time stability results of solutions, which is very important by means of qualitative theory for functional differential equations. We have considered nonlinear multi-delay system by using direct explicit representation of solutions and properties of multi-delayed perturbations of Mittag-Leffler type matrix functions and asymptotic expansions or asymptotic behavior of two-parameter Mittag-Leffler functions. Also, we give some comparisons between our results and existing results proposed by Wang and Luo in 10. While there are several papers on the finite-time stability results for first-order differential equations with multi-delays, Medved, Pospisil, Wang, Luo, but there are very few works dealing with fractional-order differential equations with multiple delays involving non-permutable matrices. The lack of qualitative analysis of the solutions of this class of delayed fractional order systems motivates us to develop new results in the analysis of this type of equations. And the main contributions of our work is as follows. We established an explicit representation of solutions to linear Caputo fractional differential equations with multi-delayed perturbation of Mittag-Leffler type matrix functions. This is linear case. Then we prove a fixed point theorem on the global existence and uniqueness solutions for nonlinear multi-delay system in the weighted space of continuous functions. Also, we provide sufficient conditions for stability in sense of finite time stability for semilinear fractional order multi-delay differential systems with pairwise permutable and non-permutable matrices. Okay, first of all, we are starting with linear homogeneous fractional order time delay system. Here GT is 0. Firstly, we need to find a fundamental solution of the homogeneous system. What is the fundamental solution? Let X is vector and satisfying the following equation. This is satisfying the main homogeneous equation, but initial conditions are unit initial conditions. At 0, this is identity matrix, and other points in from minus tau until 0, this is 0 matrix. X is called corresponding fundamental solution of the homogeneous system. Our aim first is to define this fundamental solution. The fundamental solution matrix of the Cauchy problem can be represented with the help of special delayed fractional matrix functions, which are called multi-delayed perturbation of Mittag-Leffler type matrix functions of two parameters, are studied by Mahmudov in 9. This paper exists in Journal of Mathematical Analysis and Applications. In order to determine the multi-delayed perturbation of Mittag-Leffler type matrix function with respect to multiple constant delays, we are introducing a recursive formula for QK plus 1, S1, S2, SL. Here K is 0, 1, 2, blah, blah. And A1, A0, A1, AL, sorry, are pairwise non-commutative matrices. And these matrices are satisfying the following equation. We will use this matrix equation in the verification for solution of multi-delay system. Then this is multi-delayed perturbation of two-parameter Mittag-Leffler function. And this function is convergent for alpha beta greater than 0. And here t plus is maximum 0 and t. Whenever these matrices are permutable matrices, then it will be a multinomial theorem. This is multinomial coefficients. And we will get very simple form. This is a permutable case. Of course, these ones are related to delay equations. If tau is 0, again, same results are working. In this case, we will get multiple multi-perturbed Mittag-Leffler type matrix function. Look at here. Here, this is A0 plus A1 plus blah, 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 AL power to K. So this is Mittag-Leffler type function. Another name is alpha exponential function. We know this function from special functions of fractional calculus from the books of Gronwall. That is why, for this reason, we are saying that this is multi-delayed perturbation of Mittag-Leffler type matrix function with two parameters. Then this is the auxiliary lemmas we will use. This is Caputo derivative of this function, but we have some restrictions. Related to the context of this problem, gamma belongs to open interval of 0, 1. Eta should be positive because this is domain, and from the Caputo derivative of power function, theta should be greater than 1. Under these assumptions, this formula is true. Then we will use this lemma. This is a very important lemma for main theorem. This is theorem for fundamental solution. In this case, we have two fundamental solutions, E alpha 1 and E alpha alpha. If we consider this problem with Riemann-Liouville derivative, we have only one fundamental solution, E alpha alpha. But depending on the characteristic of Caputo derivative or Caputo type differential equations, one of them should be E alpha 1, and in the integral part should be E alpha alpha. So E alpha 1 is fundamental solution of this problem. So this is satisfying homogeneous equation with unit initial conditions. Then we have proved this theorem by using the above lemma. Then there exist some situations, sometimes we can use Riemann-Liouville derivative instead of Caputo derivative. So whenever f0 or ft0 is 0, the value of function at initial point is 0, these operators coincide with each other. For this reason, we can use Riemann-Liouville derivative instead of Caputo derivative. So this is another auxiliary lemma, but there is no this type restrictions. Here, eta is positive just, not greater than 1, but gamma is real number. Whenever gamma is positive, this is Riemann-Liouville fractional derivative. Whenever gamma is negative, it will be Riemann-Liouville integral, because Riemann-Liouville fractional derivative is analytic continuation of Riemann-Liouville integral. We know this one from the lecture notes on fractional calculus. So sometimes I have used Riemann-Liouville integral, and sometimes I have used Riemann-Liouville fractional derivative. For this reason, I wrote here differintegral. So this is another auxiliary lemma. So by using these auxiliary lemmas, we get analytic representation of classical solution of this problem. This is integral representation of homogeneous problem. Here, phi s is s belongs to from minus tau I 0 and I from 1 until L. So this is prehistory function. Then, after finding the solution of homogeneous equation, we will consider inhomogeneous equation. What is the solution of inhomogeneous problem? Again, this is vector valued function for minus tau t, and continuously differentiable for positive t until large capital T, and satisfying the initial data. Here we will use superposition principle. For this reason, we will consider two different systems. One linear homogeneous system with inhomogeneous conditions, and another one is inhomogeneous system with zero or homogeneous initial conditions. In the above, we have considered the solution of 18. Our aim is to define the solution of 19. And this is particular solution of inhomogeneous problem with inhomogeneous initial conditions. So it is known that xt will be x1t plus x2t. This one will be general solution. In this case, this is the solution of Cauchy problem, of course. The solution of inhomogeneous system with inhomogeneous initial conditions. So we will define particular solution, and particular solution is defined by the following. This is convolution operator E alpha alpha t with ft. So after finding particular solution, we will find their summation. This summation will be exact analytical solution of inhomogeneous problem. Then alpha and beta equals to 1, we will get directly classical results. So this is first order multi-delayed differential equation. Here at 0, the derivative is representing the right hand derivative. So we will define multi-delayed perturbation of exponential function. This is non-permittable case. Whenever a0 blah blah al are are permutable matrices, we will get this simple formulation. So this is the closed form solution of first order multi-delayed differential equation. After finding the solution of linear problem, we will investigate existence and uniqueness problem for solutions for nonlinear fractional order multi-delay system. Here f is nonlinear perturbation, and this is continuous function. We assume that ft000 belongs to here, but for finite time stabilities, we will assume that this is 0. According to the solution of linear problem, the solution of nonlinear problem will be this one correspondingly. So then we need this estimation. This is estimation of multi-delayed Mittag-Leffler function. By using the properties of matrix construction, I have introduced it in the above, we will get this simple function. This is again Mittag-Leffler type function. Here omega is the summation of norms of matrices. Norm of A0 plus norm of A1, blah, 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 norm of AL. By using this one, we will prove the following fixed point theorem of Banach's, or well-known contraction mechanism principle. We have two sufficient conditions. One of them, nonlinear term should be continuous function. Second one, this is satisfying Gibbs condition. Then this problem has unique global continuous solution on 0t. Here we have used weighted norm. In general, for existence uniqueness problems, we are using usual norm for the space of continuous functions. Infinity norm or maximum norm or supranational norm. It has many names, but in this proof, we have used weighted norm. Norm divided by exponential function or Mittag-Leffler function. This is weighted norm. These type norms are called Bielitsky type norms. Whenever we are using a usual norm, we will get local solution in the subinterval of 0t. This is not good because we are showing that only existence of local solution. But whenever by using this type weighted norms, we can find global continuous solution of this type problems. After finding fixed point approach, we will analyze finite time stability results. What's finite time stable? A system is said to be finite time stable given a bound on the initial conditions and a certain time interval. It should be not exceed a certain bound during certain time interval. So finite time stability results are playing important role in the engineering and also mechanical physics in terms of delay differential equations. So
Excuse me?
have yes.
You just have 1 minute because
I will complete in 3 minutes. Wait, this is the definition of finite time stability. Then I have considered linear problem. This is a sufficient condition for linear problem. Then I have considered nonlinear problem. They exist two different cases. Whenever f is depending on xt minus tau I, and in this case, sufficient conditions are given the following way, and this is general case. So I have mentioned that these results are covering classical results. So whenever we will write alpha equals to 1, Mittag-Leffler function is changing exponential function, and we will get this corresponding results for classical results. And this is example, and in this example, we showed that this system is finite time stable on 0, 2. So this is the graph, and this is the reference list. That's it. Thank you for your attention. I am open for your questions in this field.
probably we have time only for one short question, if we have.
Hi, Ismail.
Yes.
I have a simple question that these type of terms with the multi-delays problem, where do they exist? Means in real life, can you give one example for that? Thank you.
Again, I did not understand the end of your question because there exist extra voices. Could you repeat, please?
Yeah, where do these type of problems with multi-delay terms exist?
You are working on existence uniqueness problems of these equations or another topic?
I'm just asking for the real life application of these kind of problems with multi-delay. Thank you.
Okay. For 1 minute, other fractional derivatives, you know, they exist many generalization of fractional derivatives. For example, Caputo or Hilbert or another ones. In terms of these fractional differential operators, you can consider this type problems. In terms of qualitative theory, you can consider exponential stability and uniform stability of these type equations. Because for classical results, these results have considered by pospecial, but with permutable matrices, not non-permutable matrices. In terms of, you can consider exponential stability results for this type equations. Also, here I have considered only matrices or with linear bounded operators. If A0 will be unbounded operator, which is infinite smooth generated of semigroup, and other operators are linear bounded operators, again, you can work this problem. In this field, I have considered it with single delay, but for multiple delays, this question is also open problem. Good luck to you.
Thank you very much. Thank you. Let's thank speaker again.
Thank you so much.
And if you have some more questions, please connect Dr. Huseynov directly.